Okay, so in this video, we're going to be continuing our work on rotational motion. Let's remember that in the first video in this series, we started talking about rotational motion. We introduced our angular acceleration, and we looked at that a little bit. And after that, we moved on to video number 2. In video number 2, we looked at sort of the equivalence of all, or the equivalent equations in rotational terms to the kinematic equations that we developed in our very first module, right? So we started off generalizing all these linear expressions or expressions that we used in linear systems to these equations that we can now use in rotational systems. So we're well equipped to deal with problems in rotational kinematics. Then in the third module, we kind of moved onward, and we started looking at rotational dynamics, right? So we looked at dynamics in rotating systems. We came up with this expression for inertia. We looked back at our definition of torque, and we wrote down our torque in terms of we ended up writing down basically our torque in terms of our moment of inertia times our angular acceleration, where I was this expression that we see here, right? And so I'm going to get rid of this to not mess up the notes, but I just wanted to mention all that because we're sort of going back through all the stuff we've already done. We did it originally in terms of linear motion, in terms of linear sort of systems, and now we're going back through and we're extending all those ideas to our rotational systems, right? So the next idea up here for this fourth video is looking at energy and work. So we're going to be looking at rotational kinetic energy and the work energy theorem again here. So we're going to start off. We're going to start off by we want to start off by generating an expression for work in terms of rotational variables, so we can look at the work done on rotating systems, right? So we're going to start off with our original definition of work that we developed a number of modules ago, right? So let's remember that work here, this is the net work done by this force acting over some distance, and the angle between the vector formed by the network and the distance is theta, right? So it ends up being F net d cos theta is our network, okay? But we know that if we assume that F net and d point in the same direction, then we have a theta of 0, and so cos theta just goes to 1, and we end up with this expression here, right? So now in the case of a rotational system, the d over which we're going to be considering that this force is acting is going to be some piece of arc length, right? And so remember, this is from several sections ago, where this is our change in arc length. This is some piece of arc length, right? So if we have some circle, let's say we have some sort of we dealt with that merry-go-round example. So imagine we have a merry-go-round again, and we're applying some sort of a force, and this thing is rotating in this direction, and it rotates. We keep applying the force here, but the object rotates until this part is somewhere up here. We've covered this section of arc. This is our delta S. Okay, so just remember what we mean by delta S here. So for some section of arc length, that's our d, right? So we can replace the d with this delta S, and this becomes our expression for work. It's the force applied over some delta S. Okay. So if we take that expression, and then we simply multiply the right hand side by 1, so we basically do nothing. We simply multiply by r over r. I'm going to isolate 1r over here, and then 1r I'm going to put under the delta S. But if we remember from before, when we were working on uniform circular motion, we saw that delta S over r is equal to delta theta, or I think we more commonly probably wrote this as delta S equals r delta theta. Oops. right? And so if we see that, then we can make the simplification that we see here, and we know from our earlier work that our F net, that's going to be our tau here for this setup, right? Where our R and our F net are going to be perpendicular to each other, right? So we don't have that sine theta because we're taking the sine of 90 degrees, and that's just giving us a 1, right? So let me clean this up a little bit. If you're unclear about any of these steps, all these sort of variables are collecting things that we've done over a number of previous modules. So if you're kind of rusty on any of those, go back and take a look at that. But in the end, after we make all these simplifications that we have outlined here, we end up with this expression that the net work done is equal to the net torque times the angle theta over which this torque is being applied. Okay, and so that's our expression for the net work done in a rotational system. We now also want to take a look at sort of the rotational analog to our work energy theorem. So we want to take a look at what our work energy theorem looks like in a rotational context. And if we remember back, as we developed the work energy theorem for linear systems, we came up with this idea of kinetic energy. We're going to again pull kinetic energy out of our development of the work energy theorem here. But in this case, it's going to be rotational kinetic energy, and we'll see sort of how that all comes to be here in a second. So we're going to start off with one of the equations that we developed 2 videos ago in our section where we upgraded all of our linear kinematic equations to rotational kinematic equations. And so if we set theta naught to 0 for one of those equations, we end up with this one here. And we can simply rearrange these variables so that we get this this expression that we see down here. And so maybe in this state, I'll explain again what we have. We have our angular acceleration. We have the angle through which this thing is changing. We have our final angular velocity, and we have our initial angular velocity. Okay, so remember what all these variables are. And we just saw that we're able to write work just up here, work in terms of our torque and the angle over which it acts, right? So keep this in mind, this equation 7, and then remember that just above we wrote down this work equals torque times theta. And we also know from the last section that we did, like just last video, that we can also write our torque in terms of I and alpha, right? And I just went over what those are, right? So if we do that, I can substitute in this expression for tau into our equation for work. We end up with work is equal to our moment of inertia times our angular acceleration times theta. And if we then take this alpha theta and substitute in the right-hand side of this equation for it, and then I distribute the I over the 2 terms that we have up there, we end up with this expression here. So we have work is equal to 1/2 I omega squared minus 1/2 I omega initial squared. And this should right away sort of pop out at people. It looks very similar to the sort of linear expression, as all of these kind of do. This is our work energy theorem written in terms of our rotational variables, right? So this is the work energy theorem, just another way that the work energy theorem pops out in a rotational context, okay? And the same way that we did for the linear system, we pulled out this kinetic energy term. We can do the same here. We called these terms in the linear system kinetic energy, and we're going to do the same thing here, except here they're rotational kinetic energy. So we have rotational kinetic energy defined down here, and if we do that, then we have a more compact way of writing down our work energy theorem here in terms of rotational variables. Our work is going to be equal to the change in rotational kinetic energy, right? If only rotational kinetic energy is changing, okay? And so we've kind of set up a few important equations here. All these boxed equations are pretty useful. So we have one here. We've got a few more down here. Our work energy theorem, our definition of rotational kinetic energy, and the work energy theorem written in its more compact form here in 13. So now that we have all these new equations and these new ideas, I thought we would do an example. So I have some numbers worked out here, but we'll work through the example. So we have a person spins a large grindstone. So this is basically like a large sharpening stone or something you could grind. Say you wanted to sharpen a knife on it or something. A large stone disc kind of. So oops, I wanted to draw it here. Okay, so that's our large grindstone. So they place their hand on the edge of the grindstone when it's not moving initially, and then they apply a force to it. So I can sort of draw that on here. Let's say we apply a force like this, some force through 1 radian of rotation, right? So we're going to go somewhere from like here to I don't know, something like this. Okay, so we're applying this force always perpendicular to the radius. This force always stays perpendicular to the radius, and it's applied over a theta of 1 radian. Okay. And so the force that we're applying has a magnitude. Well, first maybe I'll put some variables in here. So we have theta is equal to 1 radian. We have our force has a magnitude of 200 newtons. Then we're also told that r, the radius of this grindstone, is 0.32 meters, and the mass of the grindstone is 85 kilograms. Okay. And so we want to answer the following questions. First question is, how much work is done by the person in applying this force for theta equals 1 radian, right? So let's take a look at that. How do we get to this? Well, so we can easily start from this expression here. Work is equal to tau theta, right? So we can just look up here. Where was it? Right here. So work tau theta, right? So the work done is going to be equal to tau theta. So we need the torque, but we know that we can write torque in terms of the radius, the force applied, and the sine of the angle between them, right? And we still have another theta sitting out here, right? So this is just our torque. So if we have an angle of 90 degrees between our applied force and our radius, which we do here, we're taking the sine of 90 degrees. This ends up being 1, and so we end up with RF theta, right? And at this point, it's just a matter of substituting in numbers. So we can do that. We're going to end up with, well, our radius is 0.32 meters. Our applied force is 200 newtons, and we have that factor of 1 radian here, right? And so if we do that calculation, we're going to end up with 64. And what are the units on this going to be? Well, they're going to end up being joules. We know that, but we can also see that from these terms here. We have meters and we have newtons. So Newton meters gives us joules. This has no units. Radians are a unitless sort of unit, right? And so we end up with joules here. Okay. So B. In B, what do we want here? We want what's the final angular velocity of the grindstone? So we're looking for the final angular velocity. Well, we can use the kinematic equation that we started out generating our work energy theorem from to answer that. So usually we would see it like this, right? We would see omega, should be omega squared is equal to omega naught squared plus 2 alpha theta, right? Where we've taken theta naught to be 0 here, right? You'd normally see maybe like this, right? But if we set omega naught to 0, then we simply end up with what we have above. But we had no initial angular velocity, right? This was 0. This thing wasn't spinning to start off with. So we can clean this up, and we end up with omega, and we're going to take the positive root in this case, is equal to 2 alpha theta, right? And so we kind of seem to be stuck here, right? We don't know what alpha is at this point, but can we find alpha from stuff that we do know? Well, we know that we can write tau in terms of alpha if we have our moment of inertia, right? So we can rearrange this to write alpha equals tau over I. We just calculated something with tau sort of in it, so we could solve for tau in there, but we could also say, well, we know that tau in this case, because our force is always perpendicular to the radius, we know that the tau is equal to Fr, which means we can solve for our alpha in terms of Fr, both of which we already have, right? And so this means that our alpha is going to be equal to Fr over I. Now we don't know I for the object, but this is one of those sort of objects that we can just look up in our table. If we look this up in the table that we discussed a few videos ago, we can see that our I in this case is equal to 1/2. Oops. Clean that up. 1/2 mr squared, where m is the mass of our disk and r is the radius of our disk. So this is for any solid disk rotating about the axis that we have set up here. And so we can just substitute this in, and this is going to end up giving us alpha is equal to, and I'm going to flip this factor of 2 up, right? You can imagine, or maybe I'll do it in sort of not skipping any steps here. So we'll have Fr, we'll have mr squared over 2, but that means that we can flip this 2 up, right? Because basically what we can do is we can write alpha is equal to Fr over 1 over mr squared over 2, right? And if I flip this up, we're going to be taking the reciprocal of it, and so it's going to end up being Fr over 1 times 2 over mr squared, right? And if we do that, we're going to end up with 2Fr over mr squared. But here our m and our r are just the mass and radius of our disk, which we're already given. And so this is going to end up being 2Fr over mr squared, right? One of these r's is going to cancel with the one up here, and we're left with 2F over mr. Okay, that's our alpha. And since we have our alpha now, we can right away sort of substitute this back into our original expression that we had up here, right? This I'll put a dotted box around it. We can substitute our alpha into there. Ooh, and I'm bad on space here. Can I add a page? No, I can't. Okay, well, I'll just squeeze it in there. So we're going to end up with this expression for alpha being substituted back in up here. And so writing a little smaller now, we're going to end up with omega is equal to the square root of, so our alpha is becoming, well, here maybe I'll write it out fully. So we're going to have our alpha becoming 2F over mr, and we still have this factor of theta, right? And so what is this? This is going to end up being square root 4F theta over mr. Okay, and at this point we just have to substitute in numbers. We know what F is. We know that theta is 1 radian. F is 200 newtons. We know that the mass is 85 kilograms. We know that the radius is 0.32 meters. So if we substitute those in, we end up with 200 1 over 85 times 0.32. If you do that calculation, you're going to find that omega is equal to 5.42 radians per second. Okay, That's our answer for part B. And yeah, that's a bit of a problem because we also have a part C and I have no space. Okay, well, let's see if I can squeeze this in somehow. This was poorly planned out. Okay, let's try and do part C kind of like up here. Okay, so we want to find the final kinetic energy of the grindstone, right? So we know that the only kinetic energy that's going to be existing here is going to be rotational kinetic energy. This grindstone is not moving anywhere else; it's just rotating. So kinetic energy is going to be kinetic energy of rotation. And well, we just wrote down the expression for what our kinetic energy of rotation looks like. It's just 1/2 I omega squared. And we just talked about what I was, right? We just talked about it right down here. Did I write it down? Yeah, right here. 1/2 mr squared. And so we're going to end up with kinetic energy of rotation equals 1/2 mr squared omega squared, right? And at this point, again, we're ready for substitution of numbers, right? We know what m is, we know what r is, we know that our omega is 5.42 radians per second. We just calculated that. If we substitute in all those numbers, we're going to end up with kinetic energy of rotation, or our rotational kinetic energy, is equal to 1/4 times 85 times 0.32 squared times 5.42 squared. And again, if we do that calculation, we're going to end up finding that the total kinetic energy here, which is equal to the kinetic energy from rotation, is equal to 64 joules. Okay? And note that the kinetic energy that we have in the wheel now, or in the grindstone, is exactly equal to the work that we did on the grindstone. And that's not surprising, right? We put kinetic energy into this grindstone by doing work on it, and so now the grindstone has that 64 joules of kinetic energy that we gave it through applying this force to it, right? So that's the sort of first part of this. I do have sort of a second topic which I'm sneaking in here. It's still a fairly big topic, but I wanted to get it into this video because they're in the same section in the textbook, so I wanted to try and keep it as consistent as I could for you guys. So what we're going to be looking at here is the kinetic energy of rolling objects, right? So we've already seen how if we ignore air resistance, objects with the same shape, even if they have different masses, or even if they're different shapes, they're going to fall with the same acceleration, right? Ignoring air resistance. But what about objects rolling down an incline, right? Would we expect the same if we ignored air resistance and we rolled two objects down an incline? Would we expect to see the same sort of result? Should they roll down at the same pace? Well, let's take a look at that and see what ends up happening, right? So we now have two different ways of thinking about kinetic energy, right? We can think about our normal kinetic energy, right? So our 1/2 mv squared, or we talked about a new kind of kinetic energy here, kinetic energy of rotation, and we can think of that in terms of this equation here, right? So 1/2 I omega squared. Let's write that in down here. 1/2 I omega squared, right? They look similar. The sort of mass is replaced by the moment of inertia, which is pretty standard for all of our situations where we go from linear to rotational, right? And our velocity, our linear velocity, is replaced with our angular velocity. So whenever we think of kinetic energy now, we want to be thinking of it not just as translational kinetic energy, but that the total kinetic energy could have some translational part, some kinetic energy T, but also some rotational parts, so some kinetic energy R also associated with it, okay? So always think about kinetic energy as kinetic energy of translational motion, but also potentially as rotational kinetic energy. So for a free-falling object that's not rotating, right, we would expect that all of our potential energy, the potential energy initial that we have, would eventually be turned, like as this object falls, it loses that potential energy and it's turned into kinetic energy, right? So the kinetic energy final will be equal to the initial potential energy if no energy is lost from the system, right? And in the case of a falling object that's not rotating, all of that kinetic energy will be translational kinetic energy. But in the case of an object rolling down an incline, let's say it's not slipping down the incline, but it's actually rolling down the incline, right? There's now going to be, so we're going to have the same initial potential energy, and it's going to change into fully into kinetic energy by the end of this thing. Let's say this object is falling at the bottom of its fall, or sliding down a hill, I should say. At the bottom of this slide down the hill, it's not going to have any gravitational potential energy sort of left in the system formed by it and the Earth, but it will have all kinetic energy, right? Some of that kinetic energy will be translational kinetic energy, like stored up in the motion of the object, but some of it will also be rotational kinetic energy, stored up in the rotation of this object, okay? And we're going to look at an example of that here in a second, but we always want to definitely sort of keep that in mind as we're doing these types of problems. If we're dealing with point-like particles, we don't have to worry about rotation, right? But if we're dealing with objects that have some extent that are rotating as other things are happening to them, we need to be considering this rotational kinetic energy. It can sort of soak up a lot of the potential kinetic energy, or I shouldn't say potential kinetic energy. I should say kinetic energy, which can usually be used sort of only for translation, can now also be used for rotation, right? So some of the energy that before we would have thought of as being well, some of the energy that we would have thought of going from potential energy to translational kinetic energy can now be used up in the form of rotational kinetic energy. So we lose some of that additional kinetic energy that we might have had, right? So let's take maybe a look at an example here that'll sort of clear this up for us a little bit, hopefully. And so I don't have the numbers worked out, but this is directly from the text, so I'll just pull the numbers from the text. I think I have it here. Hopefully this will work. Okay, so we're looking at example 10.10 from the textbook, and this is a cylinder rolling down an incline. And we want to calculate the final speed of a solid cylinder that rolls down a 10-meter high incline. The cylinder starts from rest, has a mass of 0.75 kilograms, and has a radius of 0.04 meters. Okay, we want to assume no slipping, right? So this thing is actually rolling down this incline. It's not sliding down the incline. It's actually every bit of motion that it has to make, the cylinder has to roll through that piece of motion, right? Think of it sort of in those terms. So on its face, we might think right away, well, this is a bit of a problem, right? So we know that this is a 2-meter high incline, but we don't know how steep this thing is, right? So we can imagine this incline. Imagine an incline like this. This, we're told, is 2 meters. But we don't know how steep it is. This angle theta could be anything. This thing could be super steep like this, or it could be really, really gradual like this. We're not given that angle. So isn't that a problem? Isn't that going to prevent us from being able to solve the problem? Well, no. We're going to find in the end that it's not a problem. And in fact, we need very little to be able to solve this problem. We don't even need the mass of the cylinder or its radius. We're going to find that our solution is actually super general here. Okay, so let me start off. How would we solve this, right? So this is going to be a sort of conservation of energy problem if we think back a few chapters. How would we normally look at this? Well, we would say if we're dealing with conservation of energy, well, we would have some potential energy initial plus some kinetic energy initial. This is sort of the most general form of the first line that we could write down, right? We could even say, well, maybe there's some work non-conservative done to the system, and this has to be equal to the potential energy final plus the kinetic energy final, right? And that's fine. That's sort of the most general way we can write this out. But we know that this thing is starting from rest at the top, so there's no initial kinetic energy. And we don't have any non-conservative forces doing work here. We just have everything going from potential to kinetic energy, right? So we have no non-conservative work being done. And at the bottom, which is where we're sort of interested in looking at this thing is going to have no more gravitational potential energy or any other potential energy associated with it that we're interested in either. Okay, so our most general equation kind of boils down to this. So we have our initial potential energy, which is all gravitational. We'll sort of make that more explicit in a second. Has to end up being equal to our final kinetic energy. Okay. And now let's write out these terms in terms of variables that we're used to working with. So our initial potential energy is just going to be a gravitational potential, so that's just going to be mgh. And our final kinetic energy, well, now we need to be a little careful, right? We know that kinetic energy can come in the form of translational kinetic energy or rotational kinetic energy. So let's start off. I'm going to write down, well, maybe it has some translational potential energy or kinetic energy associated with it, and maybe it has some rotational kinetic energy associated with it, right? So we have both of our kinetic energy terms there. So to be able to solve for this, right, we need to keep in mind sort of what we're looking for here, right? So we want to find what are we looking for here? We're looking for calculating the final speed, right? So we want to get v out of this whole thing, but we have a whole bunch of variables that aren't written in terms of v. Luckily, we can change some of these variables into things that we know, right? So for a cylinder rolling, we can simplify this I right away. We can look it up, and again, we're going to find that our I in this case is going to be 1/2 mr squared. Okay, so that's our I. And if we think back to our earlier work, we know that we can write our angular velocity in terms of the linear velocity, right? We know that omega is equal to v over, and I should probably write it as a small or as a lowercase r, v over r, right? So let's substitute that in. Let's remember that our omega is coming in squared, and so we're going to end up with a squared term there. I'm going to move everything over here. So that's our initial potential energy. We're going to leave that first term as is, and our second term ends up looking like this. So we have 1/2 that was originally there. We're going to have 1/2 r squared with a v squared over r squared here, right? And so this can simplify quite a bit now. If we take a look at it carefully, we can see that this r squared and this r squared are going to go away. But also we have an m in every term, so we can go through and we can cancel out all these m's, right? We can factor out an m from the right-hand side, and we already have one on the left-hand side, cancel those out, and we're going to end up with gh is equal to 1/2 v squared plus 1/4 v squared. Okay, and obviously we can further simplify this to be 3/4 v squared, right? And so what are we looking for? Let's keep in mind what we're looking for here. Well, again, we're just looking for v. So we can isolate v now. We're just going to multiply through by 4/3 and take the square root of both sides. We're going to want the positive root here. Let's say we want a positive velocity, and so we're going to find an expression that looks like this: 4gh over 3 to the power of 1/2, or the square root of it, right? And we're basically done here. We just need to substitute in numbers. So if we do that, we're going to find v. Maybe I won't. Or yeah, okay. I'll just write in all the numbers. We'll have 4, 9.8. We're going to have, what was the height was 2 meters, and we have a 3 down here, and we're taking the square root of that. This is going to give us a velocity equal to, book says 5.11 meters per second. Okay, and so we found the velocity of this rotating object, right? we know that some of the kinetic energy has gone into its translational motion, right? So this thing works its way down the ramp, and at the bottom of the ramp, so you can imagine it started up here, rolled down the ramp, and at the bottom of the ramp, it's moving with a tangential velocity of 5.11 meters per second. It's also rolling, right? So it has rotational kinetic energy and the translational kinetic energy associated with this velocity. But it's interesting to note that if we look at this final expression here, nowhere in here do we have any mention of any angle. We don't have any mention of any mass. We don't have any mention of any radius. So this is true for any slope. This would be true for any slope that we have here. We can choose any of these, and it would be true for those. And maybe I should have drawn those in to mess up the diagram, but they're there now, so whatever. That would be true for any slope. That would be true for any radius of cylinder, and it would be true for any mass of the cylinder, right? So this is totally general for a cylinder for no slip, right? So as long as this thing is not slipping, and as long as it's a cylinder, that's the expression that's going to give us the answer that we're looking for. Okay. And so that's sort of the final example I wanted to do for this section. In the next section, we'll move on to a new topic, which will be angular momentum. And I'll see you guys there.